Today in Applied Science, I'm going to show you how I built these custom electroluminescent displays. These are made from a pane of glass, and the segments are defined by screen printing. And then I have a high voltage driver to make the electroluminescent display work. These happen to be a replica of the DSKY, the DSKY from the Apollo program. So this is what the astronauts use to interact with the guidance computer in the Apollo spacecraft. Part of the reason I haven't uploaded a video in a while is this has been one heck of a project. Regular viewers will remember at the end of last year I did a video on electroluminescent displays and another video on screen printing. And those were both in preparation to get to where we are today. So a huge multi-segment screen printed display with a pretty complicated electroluminescent driver to get all the segments working. And so you might be asking, well, why go through all this trouble? You could just get a cell phone and slip it in there and just program the cell phone to display whatever we want. And that's totally true. The purpose of doing a project like this is to learn new techniques, use materials from the period. So when the Apollo program was going, there were no OLEDs or LCDs or anything like that. So using materials of the time is cool. And then going through a whole bunch of bugs, squashing a bug that's consumed 10 or 20 hours of your life is pretty enjoyable in theory. So in this video I'm just going to describe the most interesting bugs and how you can get through this. And another benefit of me taking so long to get all this done is that I've documented everything, all of it. The firmware, the board layout, the schematics, the mechanical CAD, the screen printing graphics are all open source and on GitHub. So check out the link if you're interested. In this video, I'm going to talk about the mechanical construction of this first, then the electronics, and then the firmware last. And it's really the electronics that are probably the most interesting part about this. This, in fact, was the most difficult board bring-up I've ever done in my entire career for personal or work projects. And it was because of the high voltages involved, but not for the reasons that you're probably thinking. Like arcing was not a problem. It was much more devious than that. So let's take this apart so you can see how it's built. All of these gray pieces were 3D printed on the Form 2 printer. This is gray Pro resin. And I even printed the threads in here and just have some flathead screws holding this in. And so the original form, or the original dimensions of this DSKY unit were provided to me in a CAD document. So I actually transcribed all of this into a Fusion 360 file. And this part of it is totally original to the CAD document. And what I added was this little retainer clip here. So this comes apart like this, and you can see how this works. The retainer clip basically goes in like this and then pinches that board inside there. So there's a little ledge in here, and the glass panel goes in there and it gets pinched in. So pretty simple mechanicals there. And then you can see that there's two boards to it, and one of the boards is bonded to the glass display itself, and then the other board is the one that has the drivers. And so, of course, the first question is why go through the trouble of two boards? And that comes down to the reason for the interconnects, like basically how do we connect up to all the segments that are screen printed onto the glass, which we'll talk about in a second. If we did all of the chips and everything on one board, we would need to do blind and buried vias, because the trick is that for the interconnect layer, we need to have electrical segments on this side of the board, but we can't have any wiring whatsoever on this side of the board, or those would light up too. So basically the requirement here is that only the segments are exposed copper on this side. And so we can have wiring on this side, and we could have chips here too, but routing the whole board without vias, obviously a via would go all the way through. I suppose you could use blind or buried vias, but that's a little bit more advanced than this project calls for. There's a couple other benefits with doing two boards like this too. If we want to use the same driver board and just use a different display, like a totally different display, it doesn't even have to be a DSKY, it could be some other custom cool alien dashboard or something like that. You can just use the same driver board over and over and just plug it into whatever display board you want. The connectors are these 60-pin board-to-board connectors, and I chose these because they're relatively low density. Since we're putting 320 volts through here at most, I didn't want the pitch to be down to 0.4 or 0.5 millimeter. I believe these are 0.8. So we have enough And I think the rating on these actually is about 300 and something volts. So we're actually within spec, which is always nice. And nothing too fancy. It's just the connectors that basically hold all this together. And I've actually had pretty good luck with these connectors. They're pretty robust. They provide enough mechanical support so that the boards, you don't really need much more than these. Let's talk about the display glass itself. I guess this is kind of one of the most interesting parts of the project, or certainly the most unusual part, but I've basically had this part working for a long time and have really killed myself on the electronics, and so maybe I've forgotten how much effort actually went into this because it's been so long. But anyway, the idea is that we start with a piece of ITO coated glass, and these I bought on eBay. It's about a little over a millimeter thick. And to make an electroluminescent display, you basically want two electrodes with a electroluminescent phosphor and a dielectric between them, and then you just alternate the voltages on the two electrodes. Simple in concept. In this case, we have a common electrode, like the whole piece of glass that's coated with ITO is a conductor, and the way we access that electrically is to just use some conductive epoxy with a little wire on top. And so this wire becomes the common electrode, and then all the segments are defined by screen printing conductive ink onto here. So wherever we have this conductive ink, we'll define the electrode pattern, and that's what defines the size of the segment. There's a couple other little quirks or little details here. The original DSKY had these black screen printed words on the glass, and it also has these hard to see but little connector dots. Now I believe in the original DSKY, these little dots on the display are what they use to actually contact the common electrode. So instead of doing this conductive epoxy on here with a wire hanging off, they probably had some other method to connect to the glass itself, which was one continuous electrode through these little dots. I don't know for sure though, I never actually saw the documentation for that. But anyway, just to be visually accurate, I wanted to include them. So I screen printed these dots, and I just used silver epoxy. It doesn't even matter what they are, it's just for visual effect. And then screen printed the black wording on here. And I used epoxy black paint, which was a really good choice because later on I had to take these all apart and build them all over again. And the epoxy is so strong that I was able to use acetone to strip off all the chemical or all of the phosphor layers, but it wouldn't actually strip off the epoxy. So I was able to repaint these over and over again, yeah, bug after bug, without destroying the epoxy black paint or even the epoxy silver dots. And so I had sort of multiple chances with each one of these. Let's go through the layer stack up. So it's ITO glass, black lettering, it's silver epoxy dots. Then the phosphor layer is sprayed on to spray pattern. Then we spray on the dielectric layer, and then we screen print this black conductive ink. I looked around for quite a while to find a screen printable conductive ink and found some really expensive solutions. One company wanted like $500 for like their trial quantity of this stuff, silver conductive ink. And instead of doing that, I actually found this company, Bare Conductive, that sells their product on Amazon. And I thought it was, it's about a $20 or $30 product, and it's water-based, which I thought was a big problem. But actually that turned out to be a benefit later on. And it's, as far as I know, basically carbon dust mixed with Elmer's glue or something very similar to that. It screen prints beautifully. It's very, very thick and viscous, super, super thick, which makes it easier to screen print. The killer bug with the glass display, the one thing that really held me up with these, is that these came dirty from the factory. So when I first got these from eBay, I was very careful to never touch the surface. It came in like wrapped tissue paper, and I was really careful to not get any fingerprints on there. And then I built a few displays, and the failure mode was that the display, wherever I had a segment, it would actually rip the entire stack up off, like all the paint layers, everything would be ripped off the glass. And I thought, well, that's not fair. I mean, that means all of my adhesion is perfectly good in the stack up, but the adhesion is poor between the stack up and the glass. So then I started poking around at it a little bit more carefully and noticed that there's some kind of dirt or contamination on these glass panels from the factory. And so I held them up side by side, and you can see that there is indeed some sort of a problem. So these two panels were painted the same way, but one was cleaned and one was direct from the factory. So after making, 4 of these to start with, 4 of these glass panels, I realized I had to go back and strip them all back down to the glass and clean them and then respray them and re-screen print the electrodes. So I've probably done this a total of, I don't know, 8 or 10 times in total, so I'm pretty fast at it now. But the reason that I say I was lucky that this was a water-based screen print is because it comes off with no effort whatsoever. You just dunk them in water and it comes right off. And then the phosphor paints also come off very easily in acetone and leaves the epoxy stuff. So that was kind of a lucky happenstance. Next, we have to connect all of these screen printed electrodes to our electronics somehow. And I thought about this for a long time, like how do you connect 150 segments to your circuit board? And I settled on this idea of just using a circuit board itself. And it's okay if the electrode on this part is not perfectly continuous, because that job is being done by the screen printed electrode. So this is continuous. The electrode here doesn't have to be. So if there's holes for vias, that's okay. If it doesn't cover the whole thing, that's okay too. It just has to make some sort of contact, and it has to be within the footprint defined by the segment here. So this worked pretty well, and my first attempt was to use what's known as Z tape. So it's like an axially conductive double stick tape. This is actually pretty cool stuff. It does work. It's basically double stick tape with little metal balls suspended throughout the tape. So what you do is put the tape down and then put your other object on top. And when you crush the two together, the metal balls actually make electrical contact, but they don't short out the segments side to side because the ball is compressed top to bottom. It's not like it's conductive throughout the tape. It's literally just conductive in the Z direction. And I had pretty good luck with it. In fact, in the opening part of this video, the segment that's a little bit screwed up, it uses tape. That's actually what's inside here. It is 3M9703, and typically this comes on little segments like pieces of a roll, but I actually found these 4-inch square segments, which was pretty convenient. Anyway, so the problem that I couldn't get around with using that is the conductive tape would actually pull the segments off. Even after I cleaned the glass, the problem got much less severe, but it was still there, where it would still rip little bits of the stack up off the glass. And it was frustrating because it's kind of like, well, if the tape was not, strong enough to make it. I also had a problem where it wouldn't connect with every segment. And so if you look at that opening clip again, the segments at the bottom of the display are not fully illuminated. Like there's some that aren't making electrical contact. So I was having the problem on both ends of the spectrum. The tape wasn't good enough to make contact, but it was also strong enough that it was ripping the stack up off the glass again. So I ended up abandoning that and just going with plain old conductive epoxy. It was a little bit of I didn't even expect this to work very well, but much to my surprise, it worked nearly 100% the first time out. So I just mixed up 2-part conductive epoxy and dispensed it onto these electrode segments, and then squashed it down with the circuit board and applied a little bit of pressure and heat, and what do you know, it looks great. If I were going to build more of these or ramping up production in any way, what I would do is make another screen print mask that is a very much reduced footprint of each of these segments, and then screen print the conductive epoxy on here, and then sandwich the circuit board down on top of that. Dispensing it with the hand piece, a hand pneumatic dispenser, is fine for 1 or 2. And I was also concerned that the squeeze out would basically ruin the definition, but that turned out not to be that big of a problem. The margin of how big or small of a dollop there could be was not that bad. Okay, so we've got our glass connected to our circuit board here. All the segments are connected up to these board-to-board connectors, and we've got our common electrode here connected to the glass. So let's talk about how to drive this electrically. The driver circuit is fairly similar to the one that I used last year for my electroluminescent display projects. These are HV507 high voltage shift registers. So the idea is that you shift in a pattern of bits, and then it just makes a high voltage output for each one of those bits that you shift in. And these chips run at about 300 volts. I think the absolute maximum is 325. So if you shift in 110, you get 325, 325, and 0 volts. And you can shift in pretty quick, about 6 megahertz. And there's a latch so that when you're shifting in, the output lines don't change until you flip the latch, so you get them all to change at the same time. The thing that drives this whole deal is an AT-SAMD21 processor. This is pulled from the Adafruit M0 board, and the reason to do that is that the bootloader is already on here, so you can just connect via serial and reprogram it via serial. And the only other chip on here is this 3.3 to 5 volt converter. So in the original circuit I fudged it a little bit. These HV507 chips have a 5 volt logic rail. It must be 5 volts, not 3.3. And I just ignored that in the first circuit that I built and just gave it 3.3. And it was ever so slightly out of spec. It was almost meeting spec, but not quite. But it worked anyway, and so I just kept doing it. And then when I built this board, I was just having so many problems that I put the voltage shifter in there to eliminate that as one source of difficulty, even though in the end I don't think it made a difference. The high voltage comes from these photo flash charge ICs, and the board is laid out for 2 parallel charge paths, but that was a bad idea. I should just use one, so I only populate one set of these. In fact, on this board, if you have sharp eyes, you can see I actually pulled that chip off. So only one segment or one high voltage generator is running, not both of them in parallel. So let's talk about why bring-up was such a terrible beast on this board. I had the usual dumb problems, like for example, I forgot to put a capacitor on the reset line, and with your flinging 300 volts around, it would actually reset itself just due to coupling. Okay, so that's your standard dumb bugs. But the real killer, the thing that just absolutely made this thing impossible to solve quickly, was that it would destroy itself. So the very first time I did board bring-up, I had it set up where it would illuminate one segment at a time, and every time I clicked a button on the computer, it moved to the next segment. And so after testing, about 20 segments, I thought, oh great, this thing's working perfect. And then when I got to segment 21, I heard a faint click, and the whole thing went dead. And then upon further investigation, I realized that pretty much every chip on the entire board was blown out. 2 of these were gone, even the MCU was gone, and I didn't have a level shifter at the time. And so I thought, oh, okay, well, that pretty much makes it clear that there's got to be an arc over somewhere in there. And it's true that when I was running the driver board without it connected to the segment board, everything was fine. And so I thought, well, yeah, that means there must be some kind of, my conductive screen printing must be like really close together at some point, and it's arcing over, and then the arc causes, the whole circuit to blow out. And I spent many, many, many hours chasing this around. And then I realized that there was no arc. That definitely was not the problem. To sum it up, here's the problem. The way this thing looks electrically is like a giant capacitor that's distributed with different electrodes. So the common electrode is like one plate of the capacitor, and then each of the segments is sort of like smaller plates that are connected to the same big plate like this. And then this big plate is basically the one. So this is the common electrode, and each one of these are the segments. Now, if we want to have a really good electroluminescent display, what we want to do is alternate the voltage bipolar on these segments. So common electrode is 0 volts, the segment is 300, and then we flip them. So the segment is 0 and the common is 300. This is great because then the net voltage across the thing is 0, so there's no polarization effects. And we also get a really bright display because it's actually going through a delta of 600 volts instead of just 300. Okay, so far so good. So let's imagine a scenario where we only want one segment illuminated, say this top one. So all of these other segments and the common are being driven in phase with each other because we don't want these to emit light. So this is going from 0 to 300 at the same rate as all of these, but this top segment that we want to emit light is being driven out of phase so that we get light emitted from it. Now, what's going to happen here is all of these other segments plus the common is going to gang up against this one. So imagine that each one of these basically goes to a totem pole driver that's inside the HV507. So each one of these has like a transistor that goes to 300 volts and a transistor that goes to ground. And the chip is controlling these transistors to either dump current into or out of these lines. So there's 150 segments connected up or something, and each one of them has a totem pole driver connected to a segment. And then for the common electrode, I have 8 of them ganged together for current handling capabilities. So you have 160 of these totem pole drivers on this side of the capacitor. Remember, all these are being driven in phase. So basically, this entire bit is all being driven at the same time. So essentially 150 of these totem pole drivers against this one guy that has only one totem pole driver here. So what's going to happen, let's say the common is at 300 and the segment is at 0, and we're going to flip it. So the common is going from 300 down to 0, and the segment is going from 0 to 300. But the amount of drive strength on this side of the capacitor is much, much higher, 150 times higher. So as this thing starts to transition, the voltage on this part of the cap is going to try to be forced down to negative 300 volts, right? Because this cap was charged up to 300 volts, and now we're pulling that 300 volt side down to 0. And it's going to be pulled a lot faster, 150 times faster than this side of the cap. So what ends up happening is this point in the circuit momentarily goes very negative. And my assumption here was that the HV507 has protection diodes, which it does, and it says they have them in the data sheet. And so, you know, this whole capacitor is maybe 10 nanofarads or something like that. So certainly the protection diode should be able to dump that current safely. But for some reason, it doesn't. And so on the scope, you can see what's happening here. We're getting really negative voltages on this line in this configuration, like about, you know, negative 50 or 60 volts even. And what was happening is, without the protection diode working, eventually the voltage would get so negative that it would blow out some part of the chip and cause a low resistance path to basically dump high voltage into the control lines, and then that would propagate back through the circuit and just pop every chip down the line. Very, very frustrating. I went through hundreds of dollars worth of these HV507 chips. Oh my God, it's like I say, this is one of the most difficult board bring-ups. It is the most difficult board bring-up ever, because testing this, until I realized this is what was happening, it's impossible to test, right? Because you put it together, you turn it on and it goes click, and now everything's dead. And even if you have scope probes on there, it's not always easy to catch this in the act, right? Because if you measure any one of these other electrodes, everything looks totally fine. And if you turn on all the electrodes at once, it's also fine, because then the thing is balanced pretty well throughout. It's only when you have this electrode imbalance, this basically drive strength imbalance, that you end up with this voltage undershoot problem. Obviously, the display has to work with any number of segments illuminated. So how do we solve this? We can't change the drive strength balance because it's kind of physically set. And if we change how the segments are illuminated, you know, we can't, you know, change our minds later. So what I came up with is to do this in sort of a two-phase pattern. So in the original drive pattern, the common electrode would be out of phase with the segment electrode if we wanted it illuminated like that. And this was causing the problem. So when the common goes low, it has this massive drive strength advantage, and then causes this thing to dip negative, which is blowing out chips and wasting money. So the solution I came up with was to drive the common and segment electrodes out of phase. So in this case, instead of shifting them both at the same time, we always shift the segment electrode first. So if we have a 300 volt potential built up here, if we change the segment electrode first, it can't really cause any of this undershoot problem, because we aren't traversing across 0. So for example, if common is 300 and the segment is 0, and then we flip the segment on to 300 volts, there's no way we can get an undershoot in that circumstance, because all this stuff is staying stationary. And then when we pull common down, this thing is already charged up to 300 volts, and common is going from 300 down to 0. So there's no way we could undershoot less than 0 in that case. So we've sort of moved the problem away by just doing it in two parts, but we still get the light benefits of traversing a total of double the supply voltage. So if we kept common at 0 the whole time and just shifted segment on and off, the display would not be nearly as bright. By doing it this way, we get the brightness benefits and it doesn't blow itself up. One last wrinkle with this is the common electrode itself. So I mentioned that I have 8 I/O lines ganged together to make this common electrode for current handling capabilities. But you can tell there's going to be an imbalance here again. So we have 8 on this side, and if all the segments are on, then we have 150 on this side, and it will in fact be quite imbalanced again. And we know that the protection diodes don't work in the HV507 for some reason. So I added diodes here going, which way, and to make sure that this thing can never get outside the 0 to 300 volt supply range, and it definitely will if you don't put these diodes here. Another thing that I realized that was probably a problem is you don't want to connect these lines together directly. So if you have the HV507, you probably don't want to just gang a whole bunch of these together because the resistance is so low. If the drive strength is very slightly different between them, like the slew rates are very slightly different, these totem pole drivers aren't perfectly matched, then that means there's going to be a lot of current flow. And annoyingly, it will work for a long time, like an hour or 2 even, and then it decides to die without any reason. Like it'll just be sitting here running like this, and I figure, oh great, I've got it done now, and then an hour or 2 later and the thing kills itself. So I added some resistors so that the lines coming from the HV507 each go through their own current limiting resistor, then are ganged together with the diode protection, and then into here. So basically, all these things are just to ensure that the voltages on these lines never get outside the range of 0 to 300, or the supply voltage. And just for the record here, this one is running at maybe about 75% of its voltage, of its maximum voltage, and I've been too chicken to turn it up because this one's working so well. I can't do it just yet. So after this video, I'll try cranking it up a bit. It actually does get a fair bit brighter than this. The firmware is all written in Arduino, and it's mostly just a bunch of bit shifting. There's not, in fact, there's no libraries in here at all. And there's a bunch of control variables at the top that you can play with to change how this thing operates. I would not recommend playing with the drive pattern unless you really feel like you know what you're doing. For all these reasons with unforeseen consequences with drive strength and undershoot and whatnot, it's very safe to change all of the pixel value settings. So in the main loop, you can set pixel values to whatever you want, and that's very safe because that's not going to hurt anything. But if you change the actual shift register control loop, which does the actual bit shifting, you probably want to have some extra chips on hand when you come up with a pulse sequence that doesn't quite work. But it's kind of fun in a way. It's a real puzzle, and people solve jigsaw puzzles because it's a way to pass the time, and you learn something and feel good about it. So I'm happy with how this project turned out. I really do like how this looks, and it's running fine now. And I should also add that we can send data to it over the serial link. So the whole point of making this display is that you can integrate it with another piece of the Apollo guidance computer. And so we can connect up with USB and send it serial data. Okay, see you next time. Bye.